Hello, this is Eric from UNC Charlotte. Today, we will talk about the principles behind the MapReduce programming model. Programming a distributed memory application using a message passing framework, such as MPI, can be tedious. While MPI enables to program every aspect of the machine as you see fit, most applications may not need such a fine control over everything. In MPI, all communications are explicit. Load balancing is managed by the programmer, and race conditions and deadlocks can cause hard-to-solve bugs. MapReduce is a much higher-level programming model. It is simple to learn for most programmers as it only relies on tuples and hashing. The programming model has implicit parallelism that can scale to thousands of nodes. All questions of communications, load balancing, race condition, and deadlocks are essentially solved by the programming model. So, the programmer does not have to think in terms of parallel execution. In MapReduce, the data is represented as collections of key-value pairs. The application is expressed as functions that transform a collection of key-value pairs into a different collection of key-value pair. Key-value pairs are the fundamental objects of MapReduce, but in practice they are often tuples where some attributes serve as key. The model should be familiar to anyone who studied relational database, since it is essentially the model for a single table. There are two primary operations in MapReduce. The first one is map. It is a process where independent tasks execute a user-defined function to create key-value pairs. The tasks can be defined in many ways. They can be defined out of numbers from 0 to n. They can be defined based on file names or content of these files, or they can be defined out of an existing collection of key-value pairs. The second operation is reduce. It is the process where an independent task is run for each key of a collection. The task runs a user-defined function which has access to all the values that are mapped to that particular key in the collection. The reducer produces a new collection of key-value pairs. Let's look at two examples to make MapReduce more concrete. The first one is a batched numerical integration, where one needs to integrate multiple functions with different integration parameters. Each query is to compute the integral of a particular function f between particular bounds a and b. If one does not have a closed-form formula for the function, we may not be able to integrate it by identifying the primitive of function f. But as long as we can evaluate function f, we can use the rectangle method to decompose the integral in n chunks and compute an approximation of the integral by summing the area of each chunk. The first stage is the map task that takes individual lines of a file that contains the different requests. Each line is parsed to produce a tuple that will give an identifier for the integration and the parameters of the integral, f, a, b, and n. The value of f is just an integer that indicates which function to evaluate in a database. The second stage is also a map stage that creates one map task per tuple in the previous collection. Each task creates a tuple for each point of the integration for that integration query. In this example, the first task creates 3 tuples, while the second task creates 5 tuples. The third stage is still a map stage that creates one map task per tuple in the previous stage. This stage computes partial values of the integral and generates tuples keyed on the integral identifier. The last stage is a reduce stage that creates one reduce task per key. It takes all the partial values for that integral and sums them up. It produces the answer for each integral query. The second example consists in counting the occurrences of n-grams from the words of large texts. N-gram counting is the first step of many text analyses. An n-gram is a sequence of n consecutive letters in a word. For instance, the word mainly has multiple 3 grams, MAI, AIN, INL, and NLY. The MapReduce implementation works in multiple stages. The first stage is a map phase with one task per file to analyze. The task parses the text and extracts words, and it generates word-1 pairs. The second phase is a reduce phase, which counts the number of occurrences of each word. It generates word count pairs. The third phase is a map phase, which creates one task per word count pair. It generates for each word all of its n-grams and generates n-gram count pairs for that word. For instance, the task for quick generates 3 3-grams, and the task for in generates no 3-gram since it contains less than 3 letters. Finally, a reduce phase aggregates the n-gram count pairs that come from different words. This phase produces the total count of the n-gram across the entire corpus. We described so far the MapReduce programming model without talking about parallelism. In practice, you could even use the model to execute sequentially, but MapReduce has been particularly popular for distributed memory execution. Each map or reduce stage provides ample parallelism. Each map task is completely independent from the other map tasks in the same stage. And the only piece of information a map task needs is its own input. Tasks in a reduced stage are also completely independent from one another. The computation in a reduced task only depends on the values associated with that key. Since every task is independent within a stage, a MapReduce application can be seen as a bulk synchronous parallel application, with a strong synchronization between stages. Reductions require communication to make sure all the key-value pairs of the same key are on the same machine. But communications for the map phase is only necessary to achieve load balance. MapReduce is a programming model that uses only 2 core functions and that can scale on large systems. The simplicity of the model means that only applications with simple parallel patterns can be expressed. But its simplicity also enables programmers with no parallel programming expertise to perform analysis on thousands of nodes.